Hence, the composition of the solvent to the second stage being the same as that of the first, it is represented by point S. Okay. So, we can say this one line R 1 S is joined and point M 2, that is here this M 2, that is we can say this one using this x M 2 is equal to 0.126. So, we have got this one, that M 2, and through M 2 now we will be drawing this R 2 and E 2. Okay. This we can say this one will be getting R 2 and E 2. Okay. And from there actually we will be getting now this x 2, that will be equal to 0.15 and say y 2 will be getting as 0.105. Okay. So, we will be getting this x 2 and y 2 values, and then we will be doing this one, we will be doing again the component balance using this one, like we can say M 2 x M 2 is equal to R 2 x 2 plus E 2 y 2. Okay. So, we have this M 2, we have this 1832.97 and x M 2 we have found out that 0.126, that is equal to we can say this one R 2, that is unknown to us, we will be getting this one into x 2 we have this one 0.15 plus E 2 will be like this, the total is 1832.97. So, we can say this one 1832.97 minus R 2 into y 2 is equal to 0.105 into say 0.105. So, from here actually we will be getting R 2, that is equal to we will be getting this 855.39 kg. So, it is R 2 is equal to 855.39 kg. Okay. Then we will be getting E 2 is equal to say from this total 1832.97 minus 855.39, that is coming out as 977.58 kg. Okay. So, this M 2 we can say this one, whatever the R 2 we have, this one now is the feed to stage 3. So, we can again now for stage 3 we will be joining this S and R 3 R 2. So, we will be for stage 3 we can say, for stage 3 we can say this one, it receives R 2. Okay. And so, that is we have this one 855.39 kg and S 3 that is given in the problem, that is equal to 2625 kg. Okay. That is equal to say whatever we got this one 855.39 kg and S 3 is equal to this one. So, now we will be getting this one, from this we can say this one, whenever we will be doing this component balance for this system R 3 is say R 2 and S, and say we will be getting this M 3, that how we will be getting this one, just by doing the component balance M 3, that is we can say this mixture, that will be the summation of R 2 and S 3. So, that is M 3, x M 3 we need to get is equal to we can say R 2 and into x 2 plus we can say this one S 3 and y 3. Okay. So, M 3 that is nothing but the we can say this one summation of these two R 2 and S 3, that is coming out as 3480.39 into x M 3 is equal to R 2 is equal to this 855.39 into x 2 is equal to that is 0.15 plus S 3 is equal to 2625 and the solute concentration in the extracting solvent is already given as 2%. So, it is 0.02. So, from here actually we will be getting XM3 is equal to say point. So, it is 0.052. So, whenever we have this got this XM3 like this one, XM3 point, that is 0.052. So, now we have this point M3. So, we have this R2 and S and we have XM3. So, if we extend this one from this, we can say XC and YC axis. So, when it touches this R2S axis, from there we will be getting the point M3. Okay. So, here also this point in this mixture, this M3, it will be divided into two different parts, like this one will be R3 and another will be E3. So, from here actually we can say this one, if we read this one from R3 and E3, so we will be getting, say we can say X3 and Y3. So, that we will be getting from this graph, that we are getting this X3 that is obtained as very small value like this 0.06 this value, and Y3 that is again lower, that is we can say 0.051. Okay. So, now we have this X3 and Y3 we have. Now, we will be doing this component balance. From there we will be getting R2, R3 will be getting from there. Okay. So, we will be doing this say component balance like this M3 into, say we can see this XM3 is equal to, we have this R3 into X3 plus E3 into Y3. Okay. So, now M3 we have this one, already we have this one, say 3480.39 into XM3, actually we have got this one as 0.052, that is equal to R3 we need to find out, R3 into X3 we have got is very small value 0.06, and so we can say, and this E3 means nothing but this total minus R3, that is 3480.39 minus R3 into say 0.05. Okay. So, from here actually we will be getting R3 is equal to, we will be getting by this manipulating this equation, we will be getting this 541.39 kg, and say E3 will be getting as, say the rest of this means 3480.39 minus 541.39, that is coming out as 2939 kg. Okay. So, now we have this total x1, x2. So, we have this one x1, y1, x2, y2, x3 and y3, and r1, r2, r3, e1, e2, e3. So, we have all these parameters like this, and also we have m1, m2 and m3, means xm1, xm2, xm3. So, we have now everything with us, and also we know that the total amount of extracting solvent, how much amount of solvent is added there, and how much amount of the component say trimethylamine, that is also entered inside this extracting system. So, we know that also. Okay. So, now we will be finding that how much amount of, we can say this one trimethylamine, that is leaving the stages, means from the different stages like this. So, we can see this one total amount of trimethylamine, that is leaving the 3 stages. So, we can say will be like this, will be equal to, we can say this one E1 say Y1 plus E2 Y2 plus E3 Y3. So, that will be equal to, we can say this one E1 is equal to say 932.03 into 0.166 plus E2 is equal to 977.58 into 0.105 plus E3 whatever we got this one 2939 and Y3 is equal to 0.05. Okay. So, that this total amount is coming out as 407.3 kg. Okay. So, we can say this one this is one point. Now, so how much amount of trimethylamine is entering inside the 3 extractors with the extracting solvent. So, that is also we need to consider, but whenever we will be calculating the extraction efficiency, we need to deduct that amount from the total amount of this one trimethylamine that is leaving. From there we need to deduct that amount. So, total amount of trimethylamine. So, we can see this one entering. So, with solvent. So, there are 3 different solvent. So, we can say this one will be equal to, say we can say S1 plus S2 plus S3 into, we can say this one Ys, because for all the cases the solvent solute concentration in the solvent is same. So, it will be like this. So, we have this that these are given 815 in the problem, these are given S1 is 815, S2 is 950 and S3 that is given as 2625 kg, and the concentration of the solute in the this one extracting solvent is 2%. So, 0.02 kg. So, we can say this one, this amount we can say this one, this small amount that is 87.5 kg, this one what is called trimethylamine has entered. But we say we have seen that total 407.3 kg trimethylamine is extracted. So, we can see the effectively we can see this one. So, now we can see this one net amount of trimethylamine, that is we can say this one removal. So, will be equal to we can say this one 407.3 minus 87.5 kg. So, that is coming out as 319.5 kg. Okay. So, we can say this one. Now, how much amount of the trimethylamine was there in the total feed? So, we can say this one we had 1000 kg feed. So, we can say this one total amount of, we can say total amount of trimethylamine. So, we can say this one in the feed. So, that is we can say is equal to, we can say this one 35%. So, this is 0.35 into 1000 kg. So, we can that is 350 kg. So, out of this 350 kg, now we have this one. So, we can say this one 319.5 kg, we can these are separated. So, we can say this one fractional say trimethylamine removal. So, will be like this 319.5 divided by 350 into 100 percentage. So, that is coming out as 91.3%. So, we can say this is the fractional trimethylamine removal. Okay. So, 91.3% trimethylamine is removed. Okay. So, that was the question actually for this, this is the question for this problem. Okay. Now, we will be discussing about the continuous countercurrent multistage extraction process. So, in this case actually the feed is entering from one side of this we can say system, and with say suppose feed flow rate is f and with a solute concentration as XF, and the raffinate is exiting from the other side of this, we can say this one extraction unit. So, that is we can say this solute concentration as Xn and flow rate of the raffinate is Rn. And in that side we can say this one, from where the raffinate last raffinate actually is exiting, there the solvent actually is added. So, that with the solvent flow rate is S and solute concentration as Y s. That Y s may be 0 in some cases, then that is why it is counter currently these are flowing. So, we can say this one, the solvent extracting solvent will flow in this direction, and the ultimately the final extract will be leaving from the first extraction stage, where the feed was added, and the feed will be this moving in this direction like this. Whatever we have this one tried in this counter current cross current extraction, here we say the both the extract and raffinates are moving in the cross current direction, and say this counter current direction, but the thing is that the solvent is not added in all the stages individually. So, solvent is added in the last stage of the extraction unit. So, we can say this on a nth stage solvent is added, and this solvent actually is carried forward. So, we can say this one extract and raffinate stream flow from the stage to stage in the counter current mode and provide two final products, like we can say this raffinate that is exiting from the final stage of the extraction unit, and extract that is coming from the first stage of the extraction unit. So, for a given degree of separation, we can say this one, this type of operation requires this less number of stages for the given amount of solvent, or we can say this one this less solvent, we can say this one, say less solvent for a fixed number of, we can say stages than cross current method like this, whatever we have discussed previously. So, compared to this cross current extraction process, the counter current extraction process is, we can say, the economic. Okay. So, like this one here we will be discussing the step by step procedure also for the design of the multi-stage counter current extraction process. Before that, we need to understand the, we can say, process. So, in that case also, so we have this, we can say this binary zone like this, this is the raffinate arm, and suppose the plate point is somewhere here, and then this is the extract arm. Okay. And say it is, we can right angle triangular diagram. Now, we can say this, we will be doing the, we can say this one entire, for the entire plant like this, the for the entire system. Say we can say this one, the feed is entering at the first stage and raffinate is exiting from the last stage, where this in the last stage say solvent is added, and from the first stage extract is this one taken out. So, we will be what we will be doing this one, if we do the material balance, then we can say this one F x f plus S y s is equal to, we can say this M x m, that is nothing but this E 1 y 1 plus R n x n. So, that is we can say this one, this whatever this in the first stage, this we can say this one that is x f, that is S y s in the last stage, and then we can say this one extract is coming out from the first stage with E 1 y 1, and raffinate is exiting from the last stage, that is with the solute amount will be R n into x n. So, whenever we will be doing this, suppose if we say this one E 1 minus f means in any of the stages, if we say what is the resultant of the we can say this one flow rate, then that is nothing but we can say this one E 1 minus f, that is then in case of this we can say S minus R n. So, we will be getting always the common factor like this. So, that we now design, or we can say this one as the delta. So, this is nothing but the delta is a stream that obtained by removing a mass f of the feed from the first stage and this extract E 1, or by removing we can say this one mass R n of the last stage raffinate from the solvent S. or we can see this one in any stage. If we say this one, whatever is entering and what is exiting, what is the resultant of this one. So, we can say this one, if we do the now do the material balance in the envelope 2 like this, in the small envelope like this. So, there actually we will be getting like this R n minus 1 plus S is equal to R n plus E n. So, from here also we will be getting extract minus raffinate, that will be giving like this S minus R n. So, this is also delta. So, if we do this one repeatedly for all the stages also, we will be getting one difference, that is we can say this one say extract minus raffinate. So, that is we can say this is the delta. So, that delta actually we will be getting here. How to get this one we will be discussing in detail like this. So, since the stages are ideal, so the streams E n and R n leaving the nth stage are in equilibrium. So, we are assuming that all the stages this one we can say this one attain equilibrium before leaving the this one extraction unit. Okay. So, we can say we will start this step by step calculation procedure for this we can say multi-stage counter current extraction unit. This is very simple, very easy to understand also, and so we will be doing this one. Now, we need to draw this one, what I told actually earlier. We need to say, if we know the we can say this extracting solvent, carrier solvent and solute miscibility, then we have this ternary diagram. So, we will be now drawing this one from the we can say the equilibrium data point, we will be getting this we can say binary phase zone by drawing this we can say equilibrium line. So, this one we can say this one, suppose this is the plate point. So, left hand side will be raffinate arm and right hand side will be the extract arm. This is common to every extraction stage like this. So, now we have to draw this ternary equilibrium diagram. So, first step will be like this, we need to draw this ternary equilibrium diagram. So, this diagram may be of any type, say what we discussed this one, it may be right angular triangular diagram, it may be equilateral triangular diagram, it may be solvent free basis also. So, whatever will be this one, but for most of the this one calculations we prefer this right angular triangular diagram for convenience. We will be also discussing this one while we will solve the problem. This is a very convenient way of this one drawing this right angular triangular diagram. Okay. Then we need to locate, we can say this point feed point as well as this solvent point. So, this feed point, that is composition is already given, how much amount of the solute is there. Suppose in this case, suppose around 45% solute is present in the feed. So, it is like this x c will be 0.45, whereas this we can say this one x b will be 0. Okay. So, this is the feed point, and the solvent point, this we can say this one, that is S will be almost say we can say this one pure, or some amount of the small amount of the solute may be present. Based on that, actually it will be placing near to this we can say this one in the x b and y b axis. Okay. If it is 100% pure, then it will be touching this y axis where y axis is equal to 0, and if the y s is not 0, then it will shift towards the we can say this one this following this equilibrium diagram. So, maybe somewhere here like this. Okay. Now, we need to get this one this we need to add this f and s. So, we will be adding this one. Now, we will be getting this point M. So, M will be located. Now, we say we need to locate M, that is the mixture point. So, this mixture means if we know M, then from the component balance we will be getting suppose this x m. So, from there we will be getting this M. Okay. So, this now we need to calculate this second step will be like this, we need to calculate x m. From this component balance like this, we will be doing this f x f plus s y s by f plus s. So, if we know all these, because you see this x f and y s, these are already given in the problem, means that this one, what is the feed, we know this one, and what is the solute concentration in the feed and the solvent flow rate, and then we can say this one total amount of feed plus solvent. So, we will be getting now this x m. Okay. So, then the third stage will be like this. If the solute concentration at the raffinate of the final stage is known, like this we can say this one, if x n, that is we can say this one solute concentration of raffinate, that is leaving the last stage actually raffinate of nth stage, or we can say this one nth stage, or that is the final stage is known. Suppose this is given as this known parameter, then we can say this one, say R n and m are joined like this. So, we can say that if it is given, then we can say this one whatever the, we can say this one in the raffinate, whatever the solute concentration, suppose x n is given. So, it will be like this somewhere else, then we can say this one, we have this R n is known, suppose then x n is known, then say we can say this one, we will be adding this R n and joining m, then we will be extending to the extract arm, then we will be getting this E 1. Okay. So, we will be getting that. So, now we will be join suppose R n and say and m, then extend this one, extend the line to E 1. That is now not in, that is now in the, we can say the extract arm. Okay. Now, we have this one, f is available, we know then E 1. So, we know that this the difference point actually that we found out that suppose E 1 minus f or s minus R n, that is giving this delta. So, we can say this one whenever we have this f and E 1 we have this one. So, we can say this one E 1 minus f, or we will be getting now say s minus R n, suppose we have this s and R n. So, from there we will be getting this same delta like this. Now, we have this E 1 and f, suppose we will be joining one line, we have R n and s. So, from this we can say this one s minus R n or E 1 minus f, where it will be meeting. So, that is nothing but delta. Okay. So, from there actually we will be getting this, we can say this, from there we will be getting this difference point. So, if we extend, say if we extend f E 1 and R n s, then we will be going to this difference point like difference point. So, this delta. So, we will be getting this delta. So, for all these stages also, if we extend this one, it will meet a particular point, that is called say difference point is, that is delta. Okay. Now, the fourth stage will be like this, say draw the tie line, that is just like this one whatever we have done in the other, we can say this one extraction processes. So, we need to draw tie line, this one through E 1 and R 1 like this. We will be doing this one. So, we have now this one, say we can say E 1, we have this, if we get this, we can say this one tie line. So, we will be getting R 1. So, we will be now drawing this one like this, from here we will be drawing this equilibrium line, a tie line. So, here we will be getting this R 1. Okay. So, this is the tie line, then we will be getting this R 1 here. Okay. So, we can say this one, whenever this R 1 we have this one, it is nothing but the whatever raffinate is obtained from the stage 1, that is nothing but the feed to the stage 2. Okay. And now, we have this delta. So, if we do this one, if we repeat this one, we can say this one, say the stage 5 will be like this. Now, we have this delta point we have, suppose this is R 1 we have this one, because this is the tie line from U 1, and then we can say this R 1 and delta. So, these two are added. Now, we will be getting this E 2 here. Okay. So, then we will be obtaining this, then if these are added, then we will be getting E 2 in the extract arm. Okay. So, that will be, we can say this one. Now, again this from this we can say this we need to draw this, suppose this stage 6 will be say from E 2, again we will be drawing the tie line, then it will be like R 2. So, now what we will be doing this we can say tie line through this E 2 meets R 2 in raffinate arm. Okay. So, this is R 2, that is the feed to the stage 3. Okay. So, now we will be continuing this one, suppose this again we will be adding this R 2 and delta. So, here it will be meeting E 3, then we have again this we can say tie line, we will be getting this R 3, and that way we will be actually continuing. Okay. And then we will be getting say one time we will be reaching like this, whenever we have this R 3 we will be joining with delta, then we will be getting say now say E 4, then from there we have this we can say tie line, there we will be getting say R 4. So, that way again we will be drawing this tie line, and then we will be getting E 5, and then suppose we have this again tie line, we will be getting suppose R 5, then we will be adding this one. So, one time we will reach, actually we will be now we can say this one, we will be now continuing this one, continue this procedure till R n is obtained or reached. Okay. So, this is one this one route, actually this is we can say the very convenient route. I think we are able to this one understand the procedure for the stage calculation in the counter current extraction process. So, another the alternative technique is there, like this we can say this one alternative technique. So, what we will be doing, a line drawn from the difference point delta intersects extract arm at point actually E n plus 1, and at raffinate arm this extract arm that is in n plus 1 and raffinate arm at R n. Okay. Now, we can say this one, then second stage will be the location point like this we can say this one x c and y c plus 1, that is nothing but the is operating line. That is on, suppose this is x c and y c plane. We will be drawing this one x c y c plane also, we will be drawing this one. Then we can say, then a set of x c and y c values are derived to draw operating line. Okay. So, that also we can do this one. So, we can say this in the using this alternative technique also we will be doing this, we can say counter current multistage extraction system. Now, we have this another system, that is we can say this one continuous counter current extraction with some reflux. This is we can say this one the solute concentration in the extract leaving a counter current cascade can at best be nearly at equilibrium with the feed stream. So, it is possible to have a richer extract by the use of the reflux at the product end of the cascade. This system is similar to that of the distillation unit. Say this is the feed point location. So, feed is adding here in the fth stage, and then say this one we can remember that we can this equivalent make this equivalent like this. Say this raffinate from this fth stage will follow this route, means and then we will be getting the final raffinate from the last stage or nth stage, where the we can say this one extracting solvent was added. Like this is counter current operation, but feed is not added at the stage 1. This is added to some extent in between like this. So, to increase the we can say extraction efficiency also, and the suppose extracting solvent is added in the nth stage. So, this part is common. So, we can say this one that raffinate stripping section is common. The feed is added in between this we can say this one stages, and after that say again say suppose this extract will be following this route, and then say whatever the we can say this one another feed, or we can say this one whatever R 0 we can say, that is added in the first stage. That is nothing but another raffinate actually which that is coming, or we can say this one first stage. Some of the part actually is taken out as the product. If the situation demands like this, say if we get the time also we can explain this one. So, in that case we can say this one the reflux will be like this R 0 minus this P E, whatever the product actually we are extracting, then the difference is entering here like this one. This is the we can say this one whatever reflux is added here. So, that is coming as the feed to the stage 1. Okay. So, this is R 0 minus P E, that is we can say this one, because R 0 we have obtained from the separator of any of the system like this, where the extracting solvent actually is separated, and some amount of this we can say this extracting say what is called that carrier solvent, or we can say this one anyway if it is a feed, some amount of is taken out. So, we can say this one, this is nothing but the reflux. Okay. Now, so we will be discussing about the liquid extraction equipment like this. So, commercial extractors are of like this, generally two types like this classification based on the agitation inside this extraction unit, and we know this one also, the extraction units are mainly consisted of two different types of equipments like this. One is this mixer, another is the settler. So, we can see this type of agitation, based on that we have three different unagitated, pulsed column and mechanically agitated column, and phase contact by the centrifugal force like this. Then we can say this one centrifugal contactor, then paid by Liang and a few other also are there like this, we can say Robatel, then Delaval. These are the different names of the extraction units. Then say this one unagitated column, there are spray column, then packed column, then we can say perforated plate or sieve trays are there. So, based on the pulsed we can say agitation, we can say this one is this pulsed, then one is the packed column and this sieve tray also is there. And during this mechanical agitation, using this mechanical agitation, one is the rotary agitated contactors are there, then Sibel columns are there. These are under the after the name of the scientist like this, and then also Raston column also. Then rotating disc column, we have this, we can use this one rotating disc column in a wide range in case of this extraction. Another is the Cooney column also. This is the after the name of the scientist. And another one is also reciprocating plate column like this perforated plate or sieve plate also are there. Now, say these are the, we can say this one whatever the extraction units are there, we can now this categorize like this. We can say in general we can say this one mixer settler like this, mixer may be there, settler may be there, or tower extraction units are there also. There are also centrifugal extractors, then unagitated like this, whatever we have discussed in the previous slide. This one now again we are this one categorizing this like spray tower, packed extraction column, sieve tray, pulsed, then using this rotary agitated extraction column like this Sibel, then also Raston, then Cooney. The another one is the car column, this rotating disc contactor. I told that this is widely used in the different industries. Okay. So, thank you. So, in the next class we will be discussing about the design calculation of multi-stage counter current extraction.